Hello everybody. I would like to welcome you in the name of the European Machine Vision Association for the third webinar in a series of 4 webinars about the EMVA 1288 standard for characterization of cameras. In the first 2 seminars, we first learned what kind of effects actually degrade the signal of a camera, and we learned about the basics of the 1288 standard to quantify that in a reproducible way. Today, we will actually really turn to your application. Because if you don't know anything about your imaging application, there is such a large variety available that you cannot select a good camera. So today we will basically try to discuss together what should you basically know about your application to be able to select the best possible camera for it. What are the selection criteria? Well, the most basic thing is there is no best camera which you just can use without thinking about an application. Of course, if cameras would be ideal, then we would not have to do anything about that. But actually, it's your application which decides about the suitability of a certain camera for the usage. The questions you basically have to address are the following. The first and obviously also the quite obvious question is how much light do you have available? Is this sufficient for the camera? Then you might have scenes in which there are very dark parts and very bright parts, which means what is the dynamic range in your scene? Then, of course, different imaging applications require different spatial resolution. And so you also have to ask the question, what spatial resolution actually do I need for my imaging application? In some examples or some applications, you actually have objects at different distances. And for that, you, of course, need a certain depth of field. And so all of this is an important question. You may wonder why, because you might think, well, this has to do with the lens, but not with the camera. But we will see in a moment why this is really important to consider. Next thing is, what kind of exposure times actually are used or required for your application? If you, for instance, observe very high-speed scenes, you can only apply short exposure times. And in other applications, you may have enough time to even use large exposure times. And finally, the question is, and there we turn now to the camera, is depending on what you are going to do with your images, you might have different requirements concerning the goodness of the signal which is expressed in the signal-to-noise ratio. So what is actually the signal-to-noise ratio you require for your application? That is what you need to know. So concerning these many questions, we will basically select the 3 most important ones now and go them step by step. The first is what determines the irradiance at the image plane. So what actually, how bright can the image get at the image plane? Then we have to ask the question, what controls the depth of the field? And then we also have to investigate different applications and see what kind of signal-to-noise ratio they need. And then, as with all these interactive webinars, at the end you can ask your questions. Let's get started with the question is, we want to image an object. So the basic question is, how bright is actually an object? Well, we have to quantify the radiation which is emitted by this object, and radiation is nothing else than a form of energy. So what we have to determine is how much energy, actually, energy flux per area as it's called, more precisely, is emitted by the object. And since you are only interested basically in the light which is going into your lens, you are only interested in a certain cone of light being emitted from this object which is entering your lens. And that means you are not interested in the total radiation going away from the object, but only in the radiation going into a certain cone. And this is called basically the solid angle. So what we are interested in is how much radiation per area of our object we are observing and per solid angle is actually radiated by the object. That is basically what we need to know about the object brightness. You could express this not only in the radiance, as this quantity is called, that means in watts per square meter and per steradian, which is called a radiometric. But if you look for the sensitivity of the human eye, this is called actually the luminance, and this is then expressed in so-called photometric units, for instance, candela per square meter. However, don't use any photometric quantities. The reason is very simple. The image sensor has a different spectral sensitivity from the human eye, and so these photometric units make no sense. Just to give you a simple example, your image sensor is also sensitive in the near infrared, where the eye does not see any radiation. So actually a photometric quantity would be 0, whereas we still have, of course, some radiance measured in energy units in watts per square meter in steradian. So now we know basically how to describe the brightness of an object, and now we have to do the second step, how much light is actually received then by an image sensor. Well, here the situation is a little bit different. Here we are not interested from which direction the light is entering our pixel, but we just want to collect all the light which is entering. And so this time we describe this as an energy flux per area. That means watt per square meter. And this quantity has a different name. It's called irradiance, or the photometric term is illuminance, E. So that is actually the irradiance at the image plane we are seeking. So what we actually want to do is we want to start with the radiance of an object and answer the question, how much light do we actually receive, or what is the irradiance at the image plane? And this can be done in this schematic graph as it's shown here. We have on the left side an object area with a radiance of L, then a cone is entering our lens, which is indicated by this cone of lights rays here, and then it's all the rays meet again at the image area, at the image plane in another area. And so the relation is now we want to know what is basically the irradiance as a function of the radiance. I just want to show you the result and make it plausible to you. So the irradiance, first of all, if you see in this formula on the left side, is of course proportional directly to the object radiance because we have a linear system. So the brighter the object is, the more radiance it has, the more irradiance we will see. But now the really interesting question is, what parameters of a lens are the most important thing? You may think, well, we of course are interested in that cone, so it should be just the diameter of our lens. But that's actually not the case. It actually turns out that it is a so-called aperture number, which is the most important thing, which is the focal length of our lens divided by the aperture diameter. Well, you may ask yourself, if I, for instance, double the focal length, then also the aperture, diameter of the aperture will be twice as large, and so we will receive 4 times as much light. So the brightness at the or the irradiance should be 4 times larger. But that is a wrong conclusion, because if you double your focal length, your image size will also be in linear dimension, the double size. That means in area also 4 times. So you have 4 times more radiation going into your lens, but it's going on a 4 times larger area, and this simply cancels out. So if you want to check that, you can do experiment by yourself by simply taking one lens with a certain aperture number, remove it, take another lens with a different focal length, set it to the same aperture, and then you will see the same brightness, or the image will be as bright. So the aperture number is actually going inversely proportional with the f number squared. So if you go actually from an aperture number 2.8, for instance, to 4, that means you get only half of the light. The aperture is only changed by square root of 2, but the area is going with a square. So you will get with each actually of these numbers in this series, well-known series, for instance, 2, 2.8, 4, 5.6 meets, each time you get only half of the light if you close the aperture. And then we have, of course, in this equation, some other things. We have a transmissivity of the lens. That is, again, quite easy to understand. If some light is absorbed in the lens, then you won't see it, of course, at the image plane. So the transmissivity is another parameter. Fortunately, modern lenses are quite good by all this anti-reflection coating, so that the transmissivity is actually close to 1. And then you have, of course, if you have an oblique angle, as it's shown here also in this graph, you get also some less light, because you look now at an oblique angle onto your aperture, so you see not a full circle, but only an ellipse. The object is actually far away, and also it's going oblique onto the image plane, and all this gives this famous cosine to the power 4 law. This effect again is minor because it is actually in the middle of the image. It does not influence anything. It's only this what's called the shading, the gradual decrease of the intensity towards the edge of an image. So the most important thing is there is another thing in here, which is the lateral magnitude. But actually, this is only important if you go very close to an object for normal imaging, where the magnification factor is actually close to 1. Only the aperture number basically determines then the irradiation E prime at the image plane. So you may no longer wonder, because one of the most important quantity of a lens, which is actually written on each lens, is what aperture number it has, because it determines how bright with this lens you can take an image. So next thing is, we have expressed now the irradiance in physical energy units. That means in watts per square meter. But what we are actually interested in for an image sensor is basically how much photons we actually are getting at a pixel. And the computation of the number of photons actually requires now several steps. First thing is, we take our irradiance, that means watt per square meter. We collect it during a certain time, so we multiply it with the exposure time, and we multiply it, of course, also with the pixel area. So out of watts per square meters, we have then basically watt seconds, or this is an energy unit, joule. So then we know actually if we expose our image for a certain time and integrate over a certain pixel area, we get a certain energy unit. And to get now the number of photons, all we need to know is actually what is actually the energy unit of a photon, and this is given by Einstein, which is basically this Planck's constant h multiplied with the frequency of light. But well, frequency, we are not very common with this thing. We rather think about wavelengths. And fortunately, the frequency is nothing else than the speed of light divided by the wavelengths. So the energy of a single photon is Planck's constant times the speed of light divided by the wavelengths of the radiation. And so we can just take then the energy we have collected divided by the energy of a single photon, and then we simply know the number of photons. In units which are quite useful actually for image sensors, I have written here it down, so I assume about an irradiance of in the order of microwatts per square meter. Then I have to multiply it with the wavelengths in micrometers with the exposure time in milliseconds. I do not count pixels or measure pixels in square meters, but rather in micrometers squared. And so you see then that we get some quite handy figures. That means if I have 1 microwatt per square centimeter, have a wavelength of 1 micrometer, exposure 1 millisecond, and have a pixel which is the size of 1 by 1 micrometer, I will just receive about 50 photons. So let's sum now everything up, all the steps we have done. We started with the object radiance. So the number of photons we are getting is of course proportional to how much light basically is being emitted by this object. Then comes the next thing, the effect of the lens, which is basically 1 over the aperture number squared. Then we have the pixel area, and finally the exposure time. So the interesting thing here is to observe if you, for instance, have a certain environment where the object radiance is known, what can you play with? You can play with the aperture setting of your lens. You may select either a pixel with a large area or with a smaller one, and you see immediately if you choose, of course, a pixel with a small pixel area, you will get much less photons, and that means much less signal into your pixel. So the pixel area obviously is very much of importance. And of course, the signal we receive, the number of photons we receive also depends on the exposure time. So if you have enough time, no problem, just expose as long as is required. But for any kind of application where you basically have want to catch things fast and have, let's say, only a millisecond, for instance, of time, you have a problem in collecting basically enough photons. So the higher the speed is required, the more problems you have to get enough photons. So next step is now, because is the depth of field. The depth of field is the following. You know that one object at a certain distance from our lens is exactly basically imaged only at the image plane in one certain distance. If I get either closer or if I get farther away, then I will no longer have a sharp image, and this illustrated with a blur disk here. So I showed you here 2 examples where I either went further away or closer, which produce the same circle of confusion at the image plane. Of course, we can afford some blurs at the image plane because the pixel itself has also a certain size. So we can simply argue if the blur disk is about the size of the distance between 2 pixels, we'll still see a sharp image. And if you do the calculations, you will find out that then the depth of field, that means the change in distance delta z, I can either go closer or far away, that this is, and now observe again we have the f number, is proportional to the f number. It's inversely proportional now to the magnification, and of course it's proportional to the diameter of our blur disk. That clearly means, for instance, if with the aperture number, it's quite clear. So if we close it down, we get in the same way a larger distance. So if the aperture, for instance, goes from 4 to 8, remember 8 is a smaller diameter, then we have the double depth of field. However, the magnification ratio is much more of importance. If I go basically 2 times closer to an object, that means the magnification actually quadruples, and that means that the depth of field is now only a quarter of the distance it was before. So this is the most critical influence of magnification ratio. And now we may ask, what can we learn for our application now? What we can learn is the following. Well, if we have a given task, we typically know the size of our object that's fixed. We also assume that the aperture number is fixed because, well, we have a certain brightness in our scene, and this requires a certain f number just to get enough light. So if we start with these 2 assumptions and go back to this equation again, the only way we can increase or change the depth of field is by changing the diameter of the blur disk. And that means, since the diameter of the blur disk should be about the pixel size, the only thing is we can change the pixel size. So obviously, depth of field has to do with the pixel size. And let's do some calculation about that. So if we change basically the pixel size, that changes the magnification by the pixel size, and we assume the following, that the circle of confusion, this u prime, is equal to the pixel size, delta x prime. Our sensor, if it has in one dimension n pixels, would have then a size of n delta x prime, and that means immediately that the magnification is the pixel image size, which is n times delta x prime divided by x, and this is normally very small. So now we can basically, if I go back, I can take this equation at the bottom down here and put in the magnification ratio now, which I have calculated according to this equation here. And then we get a depth of field, which is, if you go to the rightmost equation, oh sorry, I have here the aperture number is here still denoted with k, it should actually be nf. There are two nomenclatures, sorry for that. So it's still of course proportional to nf, and now it's proportional basically to the size of the object, x squared divided by n squared, and it is inversely proportional by delta x prime. That means the following. If I take a sensor with the same resolution, same number of pixels, but now decrease the pixel size basically by a factor of 2, then the magnification ratio is basically only half of it. And since this goes in with a square, still the delta set is increasing. Of course, the blur disk is also half the size. That makes only a factor of 2, but the magnification makes a factor of 4. And that means the smaller your pixels are, basically the more depth of field you can have. You can also say, well, if I still want to have the same depth of field but have smaller pixels, I can then open the aperture a little bit more to get the same depth of field and still receive more light. So you see, you can obviously play around with the pixel size to determine this ratio, how much light you get and how much depth of field you have. Let's do the conclusion, the basic conclusions here. The depth of field is inversely proportional to the pixel size if you fix basically the object size and the aperture number. Well, if you take smaller and smaller pixels, remember what said we in the beginning, if the pixel is smaller and smaller, we'll get less photons because the area is larger. So obviously we have also here a serious trade-off. We can trade in a high depth of field versus a smaller signal. So it has consequences. We will see in a moment more detailed. Now let's assume you have the same scene, but just want to double your resolution, and you don't want to get a worse signal. So basically, first we do the following. We don't change the sensor size itself. We only take twice as many pixels of the half size. Then actually, the depth of field, of course, goes down with 1 over n. So that means the more resolution you have, even here with the problem of a smaller pixel, that means less signal, you still get less depth of field. And the worst situation is actually given by the situation where you keep the pixel size constant and just double the resolution. That means you get double the sensor. That means the magnification is now also twice as large. And then the depth of resolution goes down basically by 1 over n squared. That means doubling the resolution results with otherwise constant image sensor size gives you only a quarter of the depth of field. So high resolution you have really to pay a price for. So, and now we come to the final thing about the signal to noise ratio. Because this is now placed with these other parameters which are determined by the optics. Because if we have a smaller and smaller pixel, we can collect less and less photons or then electrons, and this makes our signal to noise ratio worse. And so what you really need to do to know about your application is actually what actually signal to noise ratio do you really require. And this may be quite different for different applications. I start with the most simple application, which is simply visual observation. So you do not do any image processing, you just look as a human being onto the image, and then of course what you don't want to see is a noisy image. And then the requirement is quite clear. If the signal to noise ratio is larger than 50, that means less than 2% variation of the pixels, then you won't see any noise with the human eye. So this is a clear prescription for just visual observation. If you have a segmentation task now, then it gets much more complicated, because then you have to think about what contrast do I have actually in my image between the object I want to see and the background. For instance, let's do what you are doing at the moment, namely you want to segment black letters on a white background, so the best possible situation you can get. Under these circumstances, you have a completely dark object and a completely bright background, maximum contrast between the both. And to solve these tasks, any algorithm does this with a signal to noise ratio of about 10. So actually the requirements for this special type of application is much less stringent. Of course, if you want to distinguish an object from a background which changes only a little bit in the intensity, you have higher requirements. So again, this decides basically your application. Then if you want to do anything like, for instance, you want to measure color or color differences, or you want to do radiometric measurements, or you want to distinguish material where their spectra changes a little bit, that is hyperspectral or chemical imaging. Under all these circumstances, you typically require very high signal to noise ratios. And actually, then it's often the case, the higher the SNR it is, the better you can do the measurement. So you see, that might be quite different. In several cases, you might have basically thresholds for the signal to noise ratio. Only your sensor must be above that. And then you can immediately say, if you look in the data sheet and your sensor does not give you this signal to noise ratio, forget about it. And in other cases, you can have the better the more SNR you have, the better. So that is what I wanted to tell you today. And we come now to questions and answering sessions. So if you have any questions to what I have asked or told you today, please ask your question, and I hope that I can give you the right answer for it. Well, maybe once you type here in your question, or if you have no question, let me continue with a summary, so to say, the take-home message of today's webinar. And I want to give you 3 short answers to what you need to know about the application. I start actually with the last one, because that is often a very critical one. What signal-to-noise ratio actually requires your application? So let's start with that, because this is a number you can write down, and that is easy what you can compare with the data sheet then. Second, how much light is available. Or that means which irradiation can be obtained at an image plane. Again, you can compare that then, and this we will do in the next webinar. What kind of saturation irradiation a sensor has, and what is actually the threshold, where the absolute sensitivity threshold, is the minimum irradiation you can detect with a certain image sensor. So that if you know this, you can also immediately look up in the data sheets whether this is possible to do. And finally, there are all these complicated questions with resolution, depth of field, and all these kind of things. Why is this important again? It's important because the required resolution, the required depth of field in your application determines basically what kind of aperture setting you can use, what kind of pixel size is best for your application. And also, of course, the other constraints of the application, what is your maximum exposure time you can have. All these type of questions determine then again how much irradiation you finally get at the image plane. So tomorrow we will have our last live and interactive webinar. And we will use then all the knowledge we have gained through the series of the first 3 webinars, and we'll put together our knowledge about the standard and how basically what kind of degradations you can have in an image sensor, and the knowledge about the application, how to perform then a camera comparison in practice, using the EMVA 1288 summary sheet. So the nice thing with the newest release of the EMVA 1288 is this 1-page summary sheet, and I will demonstrate to you, given certain applications, how you can read out of this data summary sheets the most important quantities. This will be tomorrow at 4:30 p.m. Central European Time. And since it's difficult in Europe, we have switched already to winter time. In the US, you have still daylight saving times. So it's actually at 11:30 a.m. Eastern Daylight Time and at 8:30 a.m. Pacific Daylight Time. And so thank you very much for listening. And I look forward to our last webinar tomorrow, where we'll put everything together.